All right, so it's the Arrhenius equation that shows this relationship between temperature and our reaction rate, but we don't have rate anywhere in this expression. But what we have is the rate constant. So the behavior of our reaction rate and how it changes with temperature is actually controlled through the rate constant. So K is, this drives some people nuts. It's a constant that changes with temperature. So it's a constant for any given set of concentrations. It's a constant at any given temperature, but it will change its numerical value as temperature changes. So it's not always constant. So that always, someone always gets a little peeved about that. So if that's you, sorry. Like I didn't create the system, I didn't name it. Should have called it the rate, I don't know, semi-constant, you know, I don't know, who knows. Anyway, it's, before it was constant, now it's a variable. Just bear with me, all right? And so our temperature behavior is it's all bound up, it's all engulfed in K. K is what handles that. So as temperature changes, K changes, our rate changes, all right? So that's how that is taken care of mathematically. And we've talked about how temperature kind of, just as a conceptual idea, changes reaction rate. You know, the collisions are stronger, so it will increase. You cool it down, they're softer, they're less likely to cause a reaction. Well, we account for that in K. All right, and so our Arrhenius equation is K equals A times e to the negative EA divided by RT. So that's a fun little equation. Definitely no new variables for me to spell out for you at all. So A, big capital A here, that's our frequency factor. We've already talked about how K is rate constant, so let's look at the right-hand side. This is Euler's number, so this is e to the power of our negative activation energy, which you might remember from chapter 5 in 221. If you had it with me, I definitely talked about it. If not, it's the energy required to kickstart a reaction. So things don't just happen, you know, you don't just pile wood in a pile and it just catches on fire. Something's got to cause it. It's got to get hot enough, there's got to be a spark, there's got to be something. A match thrown in there. That's the activation energy, that's the push it needs to get going. And so if you remember the old energy diagrams of a chemical reaction, we start with our, well, I got that backwards. Good thing you guys are here to keep me honest. All right, we start with our reactants, so that should be an R. We end with our products. Whew. That was close. All right, we end with our products. In this case, we lost heat energy. This was a exothermic process, but we had to go through this bump first. And that's our activation energy. So we got to roll it up the hill, and then it rolls down and releases a ton of energy. And so we're going to feel warm. So this would be something like, you know, a campfire or whatever, some sort of exothermic process. That little bump, that's the activation energy. If you have my class before, hopefully that jogs your memory. If not, maybe you saw something similar. Hopefully it helps you out. But again, it's just what we need, that little jump to get things going. Reactions don't just magically start. They have to have something put into them, and they might release more energy than they put into them, or they might not. It just depends on if they're endothermic or exothermic. All right, so we got negative EA, our activation energy. And this usually has units of kilojoules per mole. And then we divide by R, gas law constant again. I told you, it just shows up all over the place. And so we're going to use the 8.314 joules per mole Kelvin flavor of it. And then T is temperature in Kelvin. So we've got our temperature, we've got our K. They are both in this formula that allows us to account for temperature's effect on reaction rate. So there's a couple things we can do with this. First thing is you got to measure K at different temperatures. So this is like you got to go through a whole kinetics lab, and you got to go through a whole kinetics lab cold, and then you got to go through a whole kinetics lab hot. And so it's a lot of work. It is no walk in the park to find this. And your values for K tend to be very noisy when you start getting outside of room temperature because there tends to be some fluctuations. You can do it in an ice bath and maybe you can get things nice. I mean, ideally you'd be like in a freezer room or something, or a hot room. But you know, when we do the kinetics lab, the water baths tend to get pretty noisy data. So this is very hard to do and do well, and it takes a lot of time. So this little line right here, this little throwaway line, is like, okay, yeah, you do a ton of work, all right, and then we do some math with it. So we take our formula through the cunning art of natural logging both sides, a little bit more complicated than addition, subtraction, multiplication, division, but if we take the natural log of both sides, we get the following. And this kind of looks like y equals mx plus b, all right? Looks like a straight, nice line. If we get a little creative with our axes, remember, mental yoga to get straight lines on a graph. That's what we're doing. So if we have our y-axis obviously be natural log of k, and our x-axis clearly be 1 over t, because this whole thing, 1 over t is our x, this natural log of k is our y. If we plot that, we get a straight line. Our intercept will be the natural log of our frequency factor a, big capital A over there, or right here. And our slope will be equal to negative EA over R. And so our activation energy, we can find activation energy with our Arrhenius equation. So we're like, what's the activation energy for a reaction? This is one of the ways we can figure it out. This is how we determine it. How do we figure out what that little bump is to get things started? This is what we do. We do the reaction, we measure the rate at different temperatures, and then we get this noisy value out at the end. And so our activation energy is negative R times the slope of our line. Slope of our line has units of Kelvin. Heads up on that if you have to work one of those problems. And so EA comes out to be, in this case it's joules per mole. You might have to convert to kilojoules per mole if SmartWork wants you to. Just a heads up on that. So we can plot a graph, or we can compare two data points using the following equation. So if I divide ln of k1 by ln of k2, I get this. I leave it to the interested observer. I'm gonna pull an old graduate school trick. I'm gonna leave it to the interested observer to prove this relationship if you're so interested. All right, so I kicked something over here. What was that? There's not supposed to be anything else with me in the room. I got all my keys. Okay, whatever. Ln of k1 divided by k2 equals EA over R times 1 over t2 minus 1 over t1. You can use this, you can solve for, if you know k at one temperature, you can figure out k at the other if you know EA. Or if you know two k's, two temperatures, you can figure out EA. You guys know the drill. And then the other detail is you can use this, you can solve for EA, and then you can go back and you can solve for A. So just a heads up on that. So you can figure out EA and A from two data points. If I measure K at one temperature and K at another temperature, boom, boom, I can solve for EA. And then I can solve for K at any temperature. Just so you realize that. But that's really all there is to this, and that's kind of the first idea to take away, I guess. How do we account for temperature in our rate laws? It was there the whole time. It was hidden from you. It was the sneaky guy right here. It was in the constant. Who knew? Different temperature, different constant. That's why I kept writing temperatures earlier. Like on the example data sheet, we had to figure out the rate law. I wrote at 298 Kelvin. Because if we started measuring those numbers at different temperatures, we had a data sheet we couldn't use. We had a pile of garbage. Not a pile of data, a pile of garbage. So just a heads up on that. So it's been hidden from me the whole time, but now you know how temperature affects things and our mechanism mathematically for that. And then a whole bunch of stuff to play around with. Enjoy, have fun, go play in the sandbox. All right. If you haven't noticed already, Wolfram Alpha is a good website for this stuff. Just a heads up if I haven't made that clear already. I know I've dropped a hint in a practice sheet or two, but you really might want it for this stuff. Yeah, so you can plot in Excel or whatever. There's probably some other tools.